So our topic for today is Open Run deployment. So this is a generic or agnostic approach in deploying an Open Run. So we will discuss three main items here: network architecture of Open Run, um, radio network planning and design, and network deployment. So some samples of network deployment. Okay, so let's start with the network architecture. Okay, so as we move along in the discussion of Open Run, so we have discussed the difference between an Open Run and a traditional run. Okay, so definitely for the Open Run, for the traditional run, this is the way we normally deploy and open a radio access network or cell site. So for a traditional run, so there's a protocol stack that runs on a proprietary hardware. So what we do right now in our network, or most of the network that we have, especially in this country, so we have the BBU, and you have the proprietary front haul, and the RRH or the RRU. RRH meaning remote radio head, and BBU is a baseband unit. So the proprietary front haul is what we call the CPRI, or the common public radio interface. And then we have an agnostic component here. So it's a passive component. We call it the antennas. So most of the time we have three sectors or three antennas on the top as a fundamental specifications for a traditional RAN. So deploying a traditional RAN is most of the time it's single vendor. So they provide from the remote radio unit, the proprietary front haul, and to the BBU. Okay. Now for the Open RAN, so now there's a new movement of implementing a radio access network. So it's called an Open RAN. So in terms of hardware parts, so instead of using a proprietary BBU or baseband unit, so we are deploying this kind of servers. We call it the COTS, or commercial off-the-shelf servers. And the BBU was also split into two. So there's a distributed unit which handles the lower processing of the baseband, and the CU on the higher level. So the centralized unit. And then we also incorporating a RAN intelligent controller. So last week, Engineer Joel Nuesca mentioned that the concept of RAN intelligent control is not new. So during the deployment of GSM in 2G, we also have this similar intelligent controller, but not that intelligent as we are speaking today. So we call it the base station controller, or the BSC. And the counterpart of the BSC in the 3G was the region network controller. Okay, so they remove the controllers in the 2G, 3G, in the LTE, and then here in the Open RAN, they're trying to bring it back again. Okay, and then if the system would be using a massive MIMO, so there will be an integrated RU and active antennas on site. Okay, so the interface from this RU going to the DU is an open front haul. Okay, so now it's an open mechanism, so that we can mix and match our RU to the DU, and at the same time for the DU and the CU. And of course, it will be operating on software-defined technology. So you can buy a proprietary software from other vendor to work it inside these COTS, or commercial off-the-shelf servers. And we have seen that the benefits of Open RAN, as we discussed last week, so that there will be a diverse vendor ecosystem, new innovation models introduction. So meaning on the diverse ecosystem, so you will have a lot of choices. Okay, from vendor A to vendor X, no, or Z. And then operators don't need to wait for an upgrade or additional features, so they can develop also if they also have the software-defined technologies. And the main one of the main objective is to lower the total cost of ownership. So last week there was a, a study done in 2018 to 2019 that the total cost of ownership of Open RAN during that days was still high. That is expected because there's still a few um, operators are deploying. So the cost of manufacturing the equipment is still high. Now, the reason why we are promoting the deployment or use of Open RAN is to grow, no, the uh, the ecosystem. So once we have a lot of operators or players deploying Open RAN, so the manufacturing cost of the chipsets of the equipment will go down. So that eventually what we are targeting is to lower the total cost of ownership. And there are also some challenges in deploying an Open RAN. So that includes the network performance. Okay, so some of the critics are are arguing that the performance of the Open RAN is not comparable, no, to the traditional RAN. So this is a common concern regarding Open RAN and the ability to match the performance of these proprietary hardware platforms. But if you will see, especially in the US, the recent lab trials and live deployments, particularly in the Dish network and also in Rakuten in Japan, this concern has been addressed at the end of uh, at the at the end of their deployment or during their deployment. This shows also the proof that Open RAN is meeting some performance objectives, especially on the download or the upload and even the latency. Fault management, since you are handling different vendors, okay, so when something goes wrong in the network, so isolating the component that is the source of the problem can be more complex in an Open RAN environment. So to solve this problem or challenge, so there's a lot of network management tools that have been developed for Open RAN. And you will see also if you will look at the ORAN Alliance, so there are OTICs, no? So operations testings and integration centers that before a certain or an operator deploy an Open RAN, so they are doing this badging and certifications to ensure that these modules or these components will operate with each other. Okay, and in terms of challenges or in terms of fault management, you can readily identify uh, who will contribute to uh, to the problem, and you can also have a speedy issue of the resolution. Okay, and then network automation. Okay, so to fully realize the benefits of Open RAN and to manage complexity, operators must, of course, invest in the cloud management technologies and also extreme automation, including orchestration using the SMO and the zero touch provisioning. So meaning it will, if you want to define a certain element in the network, so you don't need to go on site. So there's this kind of mechanism or automation. And of course, oh sorry, and of course, uh, people need to understand the Open RAN ecosystem. So this is one of the biggest enhancements, no, to Open RAN uh, to end the vendor lockdown age. But in introducing an Open RAN, so there will be a new environment. So there will be a lot of vendors that will appear to supply hardware and software for each element of the network. And for this reason, it's very important for us, for everyone, especially for engineers like us, to be involved and to become aware of all the new hardware and software that currently exist. So it's just like upgrading. If you're have experience in handling the existing networks right now, no, vendors like vendor H, vendor E, or vendor N, you will see that in every year or every 1.5 year, they're releasing new features. and engineers needs to become aware of those features and how to tweak the parameters. So it's same thing goes with Open Run. Okay, so it's important for us to become involved and become aware of these new features. And lastly is the new team profiles. Okay, so meaning in Open Run, so as we already communicated with everybody since the start of this movement, the lines between the world of telecommunications and the world of IT are blurred. So these two industries are starting to merge with each other. Okay, especially for those people who are purely engaged in IT. So you will realize that once you expose in the Open Run deployments, you will see that there's a lot of IT skills that you need in this kind of system. And in that case, if you're already familiar with these IT skills, what you just need to learn is the telecom part, which is the RF part as well. And the same thing goes with the telecom engineers. Now they are starting to understand IP technology, networking, cloud computing, edge computing, and right now we are all studying artificial intelligence, especially um, when it when it comes to run intelligent controller. Okay, so for this reason, one of the challenges that the companies that would like to implement Open Run, they will face to a challenge that they need to adapt their teams and they need to train their teams and to cascade the knowledge in this new way of deploying networks. That's why it's very important that as early as today, even though we don't have seen yet a concrete plan for Open Run deployment here in the Philippines, but still a good chance for us to be ready at the earliest time. Okay, because we have seen deployments of Open Run in different countries, but probably in the near future, there might be a chance for us to deploy this system in this country. Okay, so now let's take the evolution. No? How did we arrive in the Open Run system? So the evolution of the radio access network or architectures has been driven by the need for a more flexible, scalable, and of course cost-effective solutions to support the growing demand of the mobile data services. Okay, so I summarize the major RAN architectures that evolved over time. So we'll start with the traditional network. This is also known as the distributed RAN. Okay, so the distributed RAN is a traditional RAN architecture that has been used for many years. So this is the father or the grandfather of network architecture. Okay, so it consists of a separate baseband unit and the radio units, and then connected via dedicated fiber or copper cables. And this architecture has been reliable and efficient, but can be expensive and difficult to scale. Okay, and yeah, we have the core network, and then the baseband and the radio unit are located in cell site premises. So whenever you want to deploy or upgrade a new component or a capacity augmentation. So you need to go on site to upgrade the baseband or to replace the radio unit. Okay. So this is the the distributed unit or the traditional network. Okay. The next, the radio access network moved from the traditional network to the centralized network. So in this case, what happened? So this architecture emerged. So in the response to the need for a more flexible and cost-effective solutions. So it uses a centralized processing unit to support multiple radio heads. Okay, so there's a lot of so what we did is that we pulled all the baseband into what we saw called the central office. Okay. So in other textbooks or other resources, you will see this as a baseband hotel. Okay, so buti pa ang baseband, hotel. Yeah. So baseband hotel. Um, and then what you can see on in the cell site premises is the radio unit, no? So this will improve, no, the flexibility and cost effectiveness of the solution. Just imagine if you will upgrade the site, so you don't need to go on the cell site premises. You just need to go on the central office, do the upgrade there, and then that's it, no. But the challenge here comes is the connectivity. So you need to have a fiber optic running from the baseband pool going to your remote radio unit. So in other countries, they use what they call the dark fiber. Okay. So when we say dark fiber, these are the fibers that the operators have laid but currently not being used. So maybe they lay it down there for future use or for capacity enhancement. That's why it's called dark fiber. There's no light not traveling inside that those fiber optic cables. So to maximize those laid out fibers, so they use it to connect the radio unit going to the baseband unit. Okay, so this approach can help to reduce cost and improve network efficiency, and particularly in areas with high density and coverage requirements. So this is what we call the CRAN as well, centralized RAN. And then we move on to the virtualized RAN. Okay, so sorry, no. Every now and then I'm muting so that I'll give time for me to have some air to breathe. Okay. So virtualized network. So right now, what happened in this architecture, it builds on the benefits of the CRAN. So it emerges from the CRAN itself, from here, from the centralized RAN. Remember, in the centralized RAN, you are still using a proprietary baseband, including the hardware. Okay. But in the virtualized RAN, what happens is that the baseband pool has still baseband, but it becomes virtualized, meaning operators can use a commercial off-the-shelf server like the one that you can buy in Dell or HP or a high-performance server, and then you virtualize a functionality of the system. So when we say virtualize, as we have discussed also during the virtualization or software-defined networking. So if you're not so familiar with virtualization, just imagine during the time when you want to listen to radio, for particularly an FM radio. So what you need to do there back then was to buy a physical radio, right? So you need to buy a physical radio and then tune into your favorite radio station and then listen. But right now, the functionality of the radio itself has been digitized. No? So we just use the word digitized. So it becomes an application. So if ever in this time you want to listen to a radio station, you just download the app on your mobile phone. Okay, so meaning the functionality of the radio is now in digital form. So similarly, that's what's happening in the baseband unit now. So the functionality of the baseband unit has been virtualized, and then you embed it in this commercial off-the-shelf server. Okay, but in the virtualized run, many says that it could be an open run, but it's not, no, because the openness of the system is still not there. Okay, although you are using a COT server, the software is still proprietary, but the front hole itself, it's not open. It's still proprietary. And the remote radio unit, it's still proprietary. Okay, so you cannot mix and match other equipment. What just happened here is that you just virtualize the baseband and then use the COT server. Okay, So this is the virtualized run, or the what we so called the VRAN. And then moving on to this concept, okay? Moving on to this concept of Open RAN. So this is the latest um, movement, no, or evolution in the radio access network. So this is based on open standards and interfaces. Now, what happens here is that it adopted uh, the strategy in the 5G network, no, where the baseband unit has been split into two: the centralized unit and the distributed unit, which was driven by the different use cases of 5G, like the enhanced mobile broadband, massive machine type communications, and the ultra reliable and low latency communications. So if you have different use cases that requires different requirements, the network, so that means you need to have a very flexible network in terms of software and in terms of location of each component. Okay, so now if the functionality of the baseband unit can be changed physically to each other, okay, so if you want to have a lower latency, you need to put the part of the distributed unit near to your subscriber. If you want to have a high data throughput, okay, you can put multiple distributed unit in that area, and then you can separate the control unit and the user plane system of, of your network. So that flexibility opens up during the deployment of Open RAN. And that was also adapted in the 5G, and that was also adapted during the Open RAN deployment. Okay. So Open RAN is also called a disaggregated RAN. Okay, so meaning the hardware is disaggregated or separated from the software, which was already done in the world of IT. So they did it already in the core network. So what they did, this movement has been brought down to the radio access network. Okay. So overall, the evolution of the RAN architecture has been driven by the need for more flexible, scalable, and cost-effective solutions to support the growing demand of the mobile data services. Okay, so these are the main uh, um, milestones in the evolution of the radio access network. Okay. Okay, so now we'll focus on the Open RAN. So we already know that the Open RAN means open radio access network. Okay. So I hope at the end of our session during the post-test, 100% of the participants will answer it correctly, that the Open RAN means Open Radio Access Network. So this is an industry movement that develops disaggregated. Okay, so you separate the software to the hardware and interoperable radio access network. So meaning you can mix and match different vendors that will leverage the general purpose processor hardware, like the commercial off-the-shelf servers, the white box radios, and then you will have a software-defined technologies, and of course, utilize open interfaces. So you can mix and match different equipment. So that is also based on industry standard. So what are those industry standard? Particularly the 3GPP. So there would be no difference of specifications on the 5G, especially on the radio access network, compared to the specifications defined by the Open RAN. So if the specifications is already existing, so the ORAN Alliance does not need to come up with a new specification. So what will happen is that if there are new component or new interface that will be introduced in the Open RAN, that's the time that the ORAN Alliance will create a specification, a new specification. So the key here is that there should be no overlapping of defined specifications between the 3GPP and the ORAN Alliance. Okay. So we see that the pillar of Open RAN is openness, the system, virtualization, And of course, the presence of the RAN intelligent controller is the intelligence, and of course, the programmability. Okay. So now let's see the components, no, of radio access network. So just to familiarize again, so everybody can be familiarized on the radio access network. So you have this architecture. So you have the 4G or 5G core network. And then connected to your core network is the radio access network composed of the baseband unit and the remote radio unit. And then the connection between the BBU and the core network is called the backhaul. The BBU to front hole to RRU is the front hole. And then you have the antenna. So what happens in the 5G and Open RAN, we are separating the BBU into centralized unit and the distributed unit. Now, if you look at this on a physical component, so you have the tower, you have the antennas. Okay, so you have different set of antennas, depends on your equipment, depends on your frequency. Same thing with your radio unit. So you have a specific frequency for high band and low band. Some radio units are working like a dual band. So meaning it's a high band 2100 and 1800, or there could be low band 700 or 900 megahertz or 850 megahertz. Okay. And then these are connected through a copper cable or jumper cables. And then you have the common public radio interface connected to your distributed unit. And then you have this centralized unit. Okay. And then you have this backhaul connection. So in some cases, instead of microwave, most of the deployment that we saw in the dish network, it was through fiber optic. Okay. They have what they call what they call the dark lit sites and the lit sites. The dark sites and the lit sites. Because later on we'll discuss it further. Now, if you will look at the overall component of the network architecture, the network architecture of an Open RAN system looks like this. Okay, so this is coming from the ORAN Alliance, so reference architecture. So you have the antenna, okay, deployed on the cell site premises. You have the remote radio unit, which might include the physical layer, the low physical layer. And there will be an open front hole connected to your distributed unit or the DU, which handles the high-level functions like the radio link control, the medium access control, and the high physical layer. Okay. And then this could be on the network function virtualized platform. Okay. So you have a quad server, and then you will deploy it as an NFVI or NFV. And then in your data center could be the centralized unit. Okay. Also in an NFVI platform. So the centralized unit can be divided into two. We can divide the control plane and we can divide the user plane. So the user plane is the one connected to the UPF, or the user plane function of the 5G, where the data transmission is happening. While the control plane is the one that gives control or validates or checks the authenticity of the connection so that they can allow the flow of traffic in the system. Okay. So this one is connected to the RAN intelligent controller. Okay. So this is the RIC, particularly the near real-time RIC, which is having a control loop of less than 1 second. And then in the near real-time RIC, you will see different applications, third-party applications, which we call the X apps. So the X apps that is very famous right now or getting a lot of attention is the power saving X app, the traffic steering X app, and the quality of service X app. So which is very important in terms of maximizing the resources of the operators. Okay. So in the near real-time rig, there are radio connection management, mobility management, QoS management, interference management, and of course, the artificial intelligence trained model. Okay. And this RAN intelligent controller is connected to the SMO, service management and orchestration platform. So this is where you design, you do some inventory of the network, you create the policy, also define the configuration, and you can also get the um, um, run intelligent control, the non-real-time rig, and also the R apps. Okay, so this is the overall architecture. Now, if you look at the the proposals or coming from a parallel wireless open RAN solution, so this parallel wireless is one of the players, no, in the open RAN domain. So if you look at their website, you will see this parallel wireless RAN solution. Okay, so this how they are proposing the architecture of an open RAN system. So this is a combination of deployment of all G system. All G means 2G, 3G, 4G, and 5G. Yes, we can deploy 2G, 3G as well in the Open RAN system, not only for 4G. But some of the operators are focusing more on the 4G and 5G because especially for the greenfield operators, you will see that most of them are focusing on the either 4G, 5G or 5G standalone in the case of Dish. Okay? So this is how the Open RAN solution is taking, it's what's happening. Another coming from parallel wireless, you will see the typical mobile network architecture or components of a mobile network of O-RAN architecture. In this illustration, you will see that there are still 3GPP defined interfaces. So they maintain those 3GPP interfaces and O-RAN defined interfaces. So for example, the S1 interface is still the same as a 3GPP defined interface. Okay. For the Open RAN defined interfaces, so these are still new interfaces. So O-RAN Alliance is the one responsible for defining this kind of interfaces and specifications. Okay. So this is a typical mobile network architecture. Now moving on to the RAN itself, I don't want to bombard you with a lot of technical details. Now, if you look at the logical RAN disaggregation, so this is what you will see between the centralized, inside the centralized unit, the distributed unit, and the remote unit. So this is based on the split 7.2x. Okay. So here you can see that the centralized unit or the central unit is divided into two, the user plane function and the control plane function. And the centralized unit is connected to a distributed unit. So the distributed unit has two connections as well, one going to the user plane and one going to the control plane and going down to the remote radio unit. So these are what's happening. This is what's happening in the inside each component. Okay. We don't have time to discuss everything, no? Every functions, what's happening. Okay, but this is what's the detailed, okay, um, steps or processes inside a logical RAN disaggregation. Okay. And another architecture coming from Remedo. Okay, so this is where your SMO, okay, the near real-time rig, the OE node B if you're using an LTE, okay, the separation of the CUCP, the UP, the distributed unit, the ORU, and the O cloud. So this is where you can see the O cloud and the corresponding interfaces as well. And then you can see also there's a lot of interfaces happening here, including the FCAPs. Okay. Okay. So includes the fault management. Okay. Okay, fault management and other policy enrichment information. Okay. Yeah. So the FCAPS is used for the configuration, reconfiguration, discovery, registration, versioning, or monitoring. So whenever there's a new policy in the network, it will go down to the near real-time rate and then communicate it with the XApps and the artificial intelligence model. So that's why the near real-time rate has less than 1 second control loop so that it can drive down the policy going to the E2 nodes. So the E2 nodes are here. So whenever you want to change parameters or threshold, so that is the function of the near real-time link. So it needs to become fast, okay? Fast so that the network or the E2 nodes can react to the requirement of the network itself. For example, you want to steer traffic from one cell to another cell, so the near real-time link must be efficient on delivering those policies coming from the SMO. Okay, so that's the overall architecture of an open RAN system. Okay, so these are the control loops only. So that's the architecture. So we have a lot of details in the architecture. And maybe once we have built the the laboratory, probably this year or maybe earlier next year, so we can define what's happening really in an ORAN architecture, and then we can read all the messages that we see in this architecture. So it's easier for us to grasp and understand what's happening if we can see it inside the lab. Okay, so we'll hold on onto these concepts, and then we'll try to study it in our laboratory in the future. All right, so now let's move on to the network planning and design of Open RAN. Okay, so we have seen that in Open RAN, if implemented well, like what they have done in Rakuten and Dish, the Open RAN technology will meet a lower total cost of ownership in comparison with traditional RAN. Okay, so last time it was shown by our speaker that in the case of Rakuten, so there's a reduction of 40% in CapEx and 30% in OpEx. Okay. Now, once we identified already the architecture, so we need to define the deployment scenarios. So we understand the architecture. So the architecture is flexible. So we don't need to deploy one size fits all architecture. So it depends on the type of deployment that we need to implement in our network. So Open RAN can be deployed using a coverage extension, densification. So if you want to extend your coverage far beyond the outskirts of your existing coverage, so you can use Open RAN. Okay, yeah, because of course there's a lot of planning needed. Okay, it's easier to say than done, no? But it's a lot of planning needed, especially if you're familiar with optimization. You know that when you deploy or overlay a different network, so there's a concern on the handover. So it's a different system itself. So inter-system handover. Okay, so that needs a specific or very critical planning. New deployments in urban and suburban solutions. Okay, so meaning you can overlay an Open RAN to an existing network using new technologies. So we have seen this in other countries where, for example, the 4G is a traditional RAN. And then when they want to deploy Open RAN, they will deploy Open RAN in 5G. So that is a new deployment. So it's on top of an existing coverage or an existing network or based on a traditional RAN. And then you will deploy Open RAN on a new technology. Okay. Or you can also replace your existing system. That is what is happening in Palau. So they have an existing network that is traditional RAN, and they will replace their system with an Open RAN system. So that's one good example. So if you want to read more about what's happening in Palau Island, so you can see that they are planning to replace their existing system using an Open RAN. Or you can do some upgrades as well. In some cases, they are using Open RAN in rural coverage because you can see that the business model or the business uh, use case in the business model in the rural is not so healthy. So if you will deploy a system that is cheaper, so it could be a solution to to have more coverage or extend the coverage in the rural areas. And of course, last week, this is one of the um, takeaways that I have validated during the presentation of our previous speaker, that we can use Open RAN to support the private network or a neutral host network. So meaning, instead of sharing only the tower or the passive components like the antenna, we can deploy a new network or new coverage using an Open RAN system by means of RAN sharing. So RAN sharing could be a MOCN, a multi-operator core network, where operators just separate the core, but from the transmission going to the frequency, it's only one operator. Or you can do a MORAN or multi-operator radio access network. So each operator will still use a separate frequency, but the radio access network is only one. So we can use that now. So instead of building a tower and then install a lot of radios from different operators, you can use a single tower and then a single radio access network. And then operators can share the existing RAN facilities. Okay, so these are the deployment scenarios. So we need to identify what are the typical deployment scenarios. And then at the end of the deployment, you will specify what type of architecture are you using in each deployment scenario. Okay, I hope you understand the logic of our discussion. So first you need to understand the architecture, how the architecture works, and then you need to select or decide on the deployment scenarios. Okay. Now, in terms of radio network planning and design, so most of the operators that we have talked to, it's the same thing. It's almost the same thing in terms of the radio network planning and process. Although there are some tweaking happening or improvement that happens that includes in the CI or the CDC CI process in terms of the software deployment. But in terms of the radio part, it's almost same. For example, no, in the typical radio network delivery process, so this is care of terahertz. So this is the one that we are discussing in one of our sessions in terahertz. So it all starts with a customer requirement, right? A business demand, a customer complaint, or a regulatory requirement. So it can happen in a brownfield network or a greenfield network. So a brownfield network is an existing network. A greenfield network is an operator with new system. Okay, so it needs to have a customer requirement. And then we'll have the map data provisioning. So they still have this map data provisioning. So to to plan where to put the cell sites or the RUs. Then after the map data provisioning, they will have initial radio network design. So they will check how many sites are needed. Okay, so in terms of coverage and in terms of capacity. Now, in terms of coverage, that would be decided by the frequency, the number of radios, antenna height, okay, antenna azimuths, okay, tilting. But the capacity in terms of the dimension comes very critical in terms of the Open RAN. Remember, we are not using anymore a proprietary baseband unit, which has this kind of a fixed capacity. Now we are using COT server. So we need to incorporate in our design the future expansion that might needed. Okay, so in terms of deployment as well. Okay, the virtualization that we need. And for example, if we're deploying 5G, what are the different slices that we want to implement? Is it EMBB, URLLC, or massive machine type communications? Okay, so that functions or factors are incorporated or added in the existing process in the radio network design. And then there, of course, there's a propagation model. So this is depicting the model of the radio environment. Right now, you will hear the what we so called the digital twin, in terms of operating in terms of open run. So when we went to NVIDIA, so they are creating this digital twin. Um, they are creating or developing this high-powered or high processing GPU that will be embedded in the DU itself or in the CU itself, to increase the processing, and then send back those send back those those data to the network so that we can create a digital twin of our network. And then, of course, site evaluation and survey, where you want to go on site to check if the location of the tower is feasible or if it can serve the target area or the coverage area that you want to serve. And then you will have a final radio network design where you will finalize what is antenna height, tower, complete tower height, azimuth, how many radios, how many baseband units, or how many CUs, or how many DUs you need. Okay. And then after that, you will design the radio parameters. So the radio parameters is almost the same as the traditional RAN. Okay, what is the power for the radio? What are the frequency assignments? Okay, so initially you need to plan for the frequency, for the PCI, for the scrambling code if there's a 3G. And then of course, you need to have installation and equipment integration. Okay. And after that is initial tuning. So you need to test using a drive test tool and of course acceptance. Okay. So this revolves inside these three main factors: coverage, capacity, and quality. And right now we are incorporating another term, which is the cost: coverage, capacity, quality, and cost. Okay, so that's the deployment. No, now if we will go in a quick view, no. So for the customer requirements, so map data provisioning is like this. So you have a planning tool, and then you have maps of a certain area, for example, Philippines or NCR, Makati region, or Bonifacio Global City. So you have a different set of maps. Okay. So after that, you will have this initial radio network design. So you will simulate what will the coverage will look like, so that you will understand how your initial design will satisfy the customer requirement or the business requirement. So this is where the radio network design is happening. Then after that, you have the propagation model. So this is what we call the there's a counterpart in OpenRAN, the digital twin. Okay. And then you go to the site evaluation and survey, where you need to go on site to check, okay, to check if there will be blocking or there are still space available on site. So some of the advanced site survey done is using a drone solution. No? So they are doing it so that it's easier for them to do site survey. And then for the final radio network design, so you will finalize how high is your antenna, what is the azimuth, okay, where is your transmission type, and then yeah, so this is essentially the final radio network design. Okay. And then after that is radio parameter. Okay, so you need to have the radio parameters ready. So the radio parameters are being done by the RF engineers, and you will give it to the installation and equipment integration team. Okay, so the integration could be done remotely. It depends on your architecture or deployment type of Open Run. Okay, so most of the time, if you will have a data center, so you will do the integration in that area. Okay, because the centralized unit and the distributed unit are located there. And after that, you will have the initial tuning. Okay, so you will have a drive test tool. You can drive around, so just to test the coverage. And after that, that's it. No? So in terms of Rakuten, they said once you put the antenna there, it's there already. And then after that, RF engineers will move to another project. And then what remains are the IT engineers. Okay. So that's why you need to learn IT skills as well. So that after the part of telecommunications is still there in the project to handle the optimization, the monitoring, and the uh, augmentations of the network capacities for quality. And then you'll have the acceptance of drive test too. Okay. Yeah, so that's basically the the overview of network design and planning. Okay. So now we move to the network deployment. So this is the last part. So how do we deploy? So we already understand the architecture, the deployment type. We know already what are the different processes in the radio network planning and design. Okay. So now the question is, how do we deploy? So what are the different deployment types of implementing? Now, if you will see the ORAN implementation options, there's a lot of I don't know ORAN implementation option. So there is what we call the disaggregated network functions, where each component, okay, or functions are completely separated from each other. So the SMO is separated from the near real-time rig. So the near real-time rig has different location. The OCU, the OCP might be located physically on different location, or probably and the DU, ODU, and the ORU and the OCLOC. So this is what we call disaggregated network functions. And in some cases, we can have an aggregated OCU CP and OCU UP and ODU. So meaning you can have this network function in one single box. Okay, especially if we are deploying, for example, LTE or 5G. Depends on the applications or use case where you want to apply this kind of implementation. Okay, so what you can see on the cell site premises is the ORU only, and this one could be on a central location. And the near real-time rig is separated from the SMO as well. So these different types of ORAN implementation. Now, in some cases, you can have also an aggregated near real-time rig, okay, where your near real-time rig is aggregated with your OCU, okay, or the centralized unit. The SMO is separated, ODU, and the RU. Okay. And in some cases naman, all nodes are aggregated. Okay, so it depends, no? It could be on a private network. Yeah. So you can have one physical box or a network in a box where the near real-time rig is there, the OCU, the ODU, and the RU. And then you have an antenna. You will just connect an antenna. So you can also deploy an ORAN implementation. So you already saw that in ORAN there's a lot of deployment. So there's a network in a box. There are open run system used for teaching purposes, and then there are also interoperability labs. So they want to test which the ORAN implementation is fit for the kind of the deployment they want to implement in the network. Okay. So moving on to other implementation options, you have the aggregated Okay. The CU is aggregated. So the CU and CP are in one box. And then yeah, that's we call it the aggregated OCU CP and OCU UP. In some cases, um, the E2 node is aggregated. The OCU CP, the OCU UP, including the ODU and the ORU. In some cases, aggregated ODU and ORU, like this. Okay, so these are the different implementation options. Now, in terms of the ORAN cloud deployment, so if you will deploy ORAN cloud in the deployment scenarios, so in a simple terms, you have the near real-time ray connected to your E2 nodes. Okay, so it depends where are these located. So in some scenarios, like for example in scenario A, we can have the near real-time rate, the OCU and the ODU located in the O cloud or edge cloud. And this ORU are located in the cell site premises. Okay. So this is one of the cloud deployment scenarios. In some cases, you can have the O cloud, okay, at the edge cloud or the regional cloud. So if you're deploying in a country level, so you have the O cloud in the regional data centers. And then you also have an O cloud at the edge cloud or for every region, okay, or for every province. And then the ORAN itself, okay, are or the RU are located on the cell site premises. So these are selected to address the initial use case for the Open RAN. Okay, so in some cases, the near real-time rig and the OCU is in the regional O cloud, and the ODU are in the edge cloud, and the ORU is still on the cell site premises. Okay, in some cases naman, the ODU is located near the edge location. So they call it, in Dish, they call it the lead sites. No? So you have a centralized DU. The DU is located on a central location. And then you will use the dark fibers going to your radio units. So we call it the scenario D. And yeah, maybe in the future, but still not yet seen. No, in terms of implementation, we haven't seen it yet. Maybe here, this is in the future, the scenario E and scenario F, where all components will be deployed using the O cloud. Okay, yeah. So that's not yet been seen, but probably this could be part of the future use case. No? So so this is due to the ORU being virtualized. Okay. Okay, so what else we have here? So yeah, so last slide would be the ORAN cloud deployment scenarios. Just another illustration where you can see the regional or the metro. So the 5G core or the EPC is located here in the regional area. So what happens in the edge? 5G core could be deployed here, regional or edge, and the cell site premises could be here. Some scenarios as well, you can put the near real time rig on an edge location or the edge server. Your control plane is in the edge because it doesn't need a lot of transmission, but there's still a latency requirement. But the control plane, the OCU-CP could be also here, and the ODU. So it depends on the use case if that requires lower latency, higher throughput, or massive connections. As I mentioned, it depends on the slice that you want to implement in your network in terms of the 5G deployment. Okay. So example for this one, that in this use case, you don't need to have a low latency communication. That's why the near real-time rig, the OCU, and the ODU are located at the edge. So ORU is only left on the cell site premises. And in terms of you don't need to have lower latency further low latency, you can put the near real-time rig in the regional or metro. And the control plane is here. Okay, and the user plane, the control plane of the centralized units here. And the ODU is on the central office. Okay, and ORU is located on the cloud. Okay, so yeah, so that's the different deployment scenarios for the Open RAN. So each operator that would like to deploy it, so they planned it in a more detailed level. Okay, because it depends on the requirement of that certain area. Okay, so for example, in the Dish Telecom, there are sites that have centralized DU, and then there are sites, particularly in the urban areas, where there's need for a high traffic demand, where the DU is near the ORU. Okay, so it depends on the type of area requirement that you would like to serve to your customers, right?